2:30, you say?
At
No,
2 o'clock.
2 o'clock.
Okay, well anyway, so questions then?
Yeah, okay. Thank you very much. I think it's always very extremely interesting and important, especially in Finland. And now you can pose questions to Professor Pasvin.
There are many ideas that come to my mind how this new model could be used to construct hard scientific arguments against uranium mines and new power plants. And we would need certain scientific data and like tabulated data about many things. And do you have interest in consulting Finnish activists for obtaining this data?
The data is available on that website. The chapter that I wrote for the ECRR report, this blue one.
Yes, but I'm talking about, let's say, some new things that are outside this model, like, let's say they are opening a new uranium mines in Finland, and we have to calculate that how much isotopes escape from the
Oh
dust,
yes, sure. Yeah. Okay. I've probably helped with that. I've given evidence to the Canadian Parliament, and I've been to Tanzania recently to talk about uranium mining. A lot of people are coming to ask me about uranium mining. One of the most powerful weapons we have is a huge computer program which was developed by the American Space Administration, which is available on the internet, in which you can calculate the dispersion of dust from any point. So you put in the geo-coordinates, latitude and longitude, and you type in various things into the program about what you want to know, and it will give you a result which you can use on a Google Earth map. So it directly goes into Google Earth, and it shows this dreadful plume of material in green and yellow and other ghastly colours in the direction of where this stuff is likely to go. So you then print that, and you use that in your argument to show that the material from these mines will go over huge populations and will cause. And you really only have to show that map, and everybody in the big population will immediately start jumping about and get scared.
Sounds very good, but it's still just one step on this ladder.
Yeah, sure.
What I want to do is to estimate, give a number that how many people will statistically die.
Yeah, sure. Well, what you do is I mean, I've done lots of those calculations. They can be done. What you do is you work out we know from ICRP Standard Man, you know the inhalation rate, so you know how many cubic meters in a year that somebody inhales, and then what you do is you have to work out the concentration in the air in terms of microbecquerels per cubic meter or milligrams per cubic meter or whatever it happens to be, which you can get from this NOAA map, right? You estimate the population inside the plume, and so you know how many people will get this amount of inhalation over what period of time, and then you have risk coefficients which are written down by the ICRP, but also in the back of this thing, and so you can work out the dose, and then multiply that by 1,000 for the ICRP for the ECRR error factor, and then that will give you a dose to the people. Then you multiply by the risk factor, and will give you the number of cancers. So it can all be done. Yeah, sure.
And then the first thing we need is the concentration of uranium in the mining.
In the air. Well, you can get that. You can get that because you can make an estimate of that on the basis of the concentration of uranium in the air at other open-cast uranium mines. That data is available. It's all a bit tedious, but if you've got the time to do it, you can do it.
And then we need to also know that how much dust gets in the air.
Oh yeah, well you can do that. There's a standard dispersion coefficient. It's all been calculated. The what's called the resuspension of dust. It depends upon whether you've got mechanical disturbance or whether you've got just ordinary situation. But with mechanical disturbance, the resuspension factor is 10 to the minus 8 or 10 to the minus 7. So if you take the number of becquerels per square meter, and then the resuspension, you multiply that by 10 to the minus 7, and that will give you the concentration in air per cubic meter. All of this, I mean, if you contact me by email, I can explain all this stuff.
But some of these mines or landmines are in Lapland. where very few people live, and the danger is that it goes into the river and goes into the Baltic.
Exactly.
So it's not only the air,
No,
so
you're
it's
right.
spreading.
You're right, and that is a much more important route, because if it gets into the Baltic, it will go all around the Baltic coast and get into the sediment, and then that Irish Sea effect that I was talking about will operate. So, and I was talking to Helcom yesterday. They don't even measure uranium in the Baltic Sea. They've never measured uranium in the Baltic Sea. Isn't that extraordinary? They measure all the other stuff, cesium, plutonium, all that, but not uranium. So next year they promise they're going to start looking at uranium in the Baltic Sea.
They would stop the same year.
They didn't promise, they said maybe, so
Yeah.
please call them and remind them. So they don't monitor uranium.
Yeah,
In
they
the
don't monitor
whole Baltic
uranium.
Sea region area, they
That's
do not
right.
monitor uranium.
And they seem quite you know, what's the word, helpful, you know, so it did sound like it hadn't occurred to them to measure uranium. Anyway, okay. So, but if you remind them that they should measure uranium, perhaps they will.
So,
About the other question about operational plants. That if the plant is in normal operation, there are the mechanisms that disperse the radioactive material out of the plant, even if it's in normal
Yes,
operation.
yes, that's right, they do.
We would need to know how much are
How
these.
much? It's all to be found in the United Nations Scientific Committee on the Effects of Atomic Radiation, UNSCEAR. If you get UNSCEAR 2000 from the library, then there's a list in the back of UNSCEAR 2000, and it will tell you all the concentrations of particulates, iodine, tritium, noble gases, the whole lot. You know, it's all there in the tables.
Plant type.
And also the operators themselves should, I think under law, they have to publish their releases. But anyway, certainly in the United Nations Scientific Committee documents, it'll give you the concentration in becquerels, terabecquerels over the year. Then of course that's all you get, you know. But you can figure it out from that. Yes. Right.
any more questions? Voitte kysyä myös suomeksi. You can also ask me Finnish if it's difficult to. Voit kysyä suomeksi, jos on vaikea kysyä englanniksi tällaista vähän hankalaa asiaa. Tai voi kysyä myös siis tästä asiasta, jota ei ymmärtänyt äsken.
Siinä on vielä aika monta mainintaa näistä verkko-osoitteista, että olisiko niitä jossakin.
Joo, niin tässä on tällaiset tiedot ollut jaossa, se on ilmeisesti tuolla edelleen. Siinä on se verkko, tuolla se lehtitiedot.
Se on tässä.
Joo, siinä. Yeah. I think that if no one's asking, I think that I must play a little bit like a devil's advocate and ask something about what some, how to say, nuclear-friendly people would ask. If you're speaking about this general increase in cancer rate in worldwide, what about this chemical exposure? It has also increased. What would you ask?
Good question. There are two answers. There are 2 points that should be made here. One is that from the point of view of human biology, chemicals I used to work for pharmaceutical companies, so I know a little about drug metabolism and the metabolism of foreign compounds. And evolution has developed the most sophisticated methods for excluding the dangers from chemicals. So there's a whole range of enzymes which destroy dangerous chemicals. I'm not saying that there aren't chemicals which manage to get through this system, but these chemicals generally are unable to affect except for very few of them, affect the DNA. They don't get to the DNA, and if they do get to the DNA, they crack off one side of the chain. So a chemical reaction is unlikely to be such that it will work on both strands of the DNA because they're too far apart, you know. So the DNA has two complementary strands, you know, one strand and then another strand. And the distance between these strands is such that a chemical reaction will not usually affect both of the strands at the same time. It will take out one strand. And that's why we've developed repair mechanisms, so that the evolution has developed these two strands so that we can repair damage to one strand on the basis of the other strand, because they're always complementary. So on one side you have one DNA base, and there's always the same DNA base on the other side, a complementary base. And so you can always repair, single strand breaks can be repaired. So that's the biological argument. And from radiation point of view, radiation, certainly alpha particle radiation and localized Auger radiation at the DNA is more like a bomb. So it's not like a chemical reaction, it's like a bomb. It goes bang, and it just blows both the strands of DNA apart. So now, instead of having this, you've got one over here, one over there. And we know that this is true because they go back and stick together. And sometimes they stick together wrongly. So if you look at people who've been affected by radiation, and you look at their chromosomes, you find these strange effects where you've got two chromosomes joining back to back, and you've got ones that join in a circle. So you have like dicentrics and centric rings. So you have ring chromosomes where the two ends of the thing that are broken, one joins here, one joins there, and you have a circle. And you can see these under the microscope. So that's the biological argument. Now the epidemiological argument is this, that in England, which I've studied England cancer for 15, 20 years. And in England, all the agrochemicals and all the chemicals that are associated with weed, insecticides and all that, are all on the east coast of England. That's where the food is grown. It's grown in East Anglia, where the land is flat and there are rivers and there are lots of good soil. On the west coast of England and in the mountains in Wales, the soil is very bad. Nobody grows anything there. So you've got two sides to England. You've got the agricultural chemical side, and you've got the high rainfall radiation side. Because of the rainfall, because it's an Atlantic coast, all the rain falls on the west coast. So so the cancer epidemic actually is on the west coast, not on the east coast. And so that's the epidemiological answer to the chemistry question, which is an important question. Because everyone knows that there's this increase in cancer, but they say, hey, it's modern living, we've got all these chemicals, but we get all the good results of these chemicals, and da-di-da-di-da. And of course, chemicals do have an effect. I'm not saying that they're great, They cause promotion. So once the cancer starts, certain chemicals, for instance, there are a lot of chemicals which are estrogen mimics. So if you have breast cancer, then the estrogen effect of these chemicals will cause the cancer to proliferate more quickly, will cause the cells to develop more quickly, the cells will divide more quickly, and the more cell divisions that there are, the more likely you are to get cancer, because cancer is more likely to occur in a cell division. So there are reasons why the chemicals are dangerous, but basically, this is my feeling on the basis of the evidence, the radiation is the cause of the cancer epidemic. The chemicals maybe help.
There was one person who all his life has been working at Stuck, He made his doctor's dissertation last year, and according to him, radioactivity is not the problem of the Baltic Sea, but the thermal pollution, the warmth that is heating the Baltic Sea, and he's one of the most sort of powerful persons at Stuck, because he has worked even before the nuclear power came. He went to Norway in '74 to assist at the composition of the lobby. So he knows all of it, and he says that he's serving the Finnish people.
Well, there's no way that thermal pollution, I can see that thermal pollution could cause cancer. I mean, it might affect the biota in the Baltic Sea, so you might get variation in fish stocks, and the substances that are eaten by the fish will change, so the different kinds of fish will. So there will be ecological effects in the Baltic Sea if it's warmer. There's no question about that. It's the same sort of thing we get with global warming all over the world. But thermal pollution can't cause cancer.
But he's not saying that. He says that radioactivity in the Baltic is no problem.
Oh,
The
well,
bigger
of course.
problem is the thermal
Oh, I
pollution,
see.
according to him.
I
That's
see.
his logic.
Well, I mean, his logic would be that the radioactivity has no effect. I mean, the Stuck logic would be radioactivity is okay, you
Yes.
know, and some of these people believe it's good for you.
Yeah.
I mean, they will come out in public and say, you know, everyone should have radioactivity because it, you know, it makes you happier. And it's not a joke. There's these scientific papers that say this shit. So.
So did you visit Stuk now here?
Yes,
during your
well, we
visit?
didn't really. We visited Helcom. I think they see us coming, you know. I think they know we're coming for them, and so they get their people in position. We came to see Hakulinen in the cancer registry, and we came to see Helcom because we wanted to get the data. We wanted to get the actual data of the pollution of the Baltic Sea right the way back to 1982, so we could see a progression of the radioactivity in the Baltic and see how it developed. And then we'll look at the cancer. So Hakulinen will give us the cancer data, and we'll look at the increase in radioactivity, increase in the cancer, and do the same sort of thing as Martin Tondel. That was the idea. But then when we went to see Helcom, Stuk was there. But anyway, I have to say that the lady who came from Stuk was delightful. She was very friendly, you know, she was kind of helpful, and oh yes, we really like you, and all this stuff. But so she was the kind face of Stuk. She was and she did say that they would be pleased for us to go to one of their conferences, and maybe we could help in this and that. So we possibly got a little way in there. They're being a lot friendly to us than they used to be, I can say that.
You spoke about false cases where this material evidence of dangers of radioactivity could be used. Are there any such cases where critics have won and they have used this kind of evidence?
Well, I have done a lot of court cases. I started doing these court cases in the United States in about 2004. And I wouldn't be here now if it wasn't for these court cases, because I'd make a bit of money out of it. You know? I mean, otherwise I would be just like all of you, you know, poor. And I wouldn't be able to come to Helsinki, that's for sure. And the point is that we win the court cases. That's the point. We win the court. So far, I win nearly every court case that I've been in to present this argument, the basic argument that I presented to you, because the truth is that if you take ordinary people, and I take you to be ordinary people, you know, I'm not talking about unordinary people. These are the guys in suits who work for Stuk, you know, or the ICRP. They will see the logic of the argument, because it's not difficult. It's a simple argument, you know. You have people who are exposed to radiation after Chernobyl, and they've all got cancer, and so on. All these situations are fairly straightforward. So if you take them in front of a jury, you win the case. But I don't usually get to a jury, actually. What happens is that as soon as I appear, they pay up the money. So the court case is won, but it's not won in a way that you can kind of get it out into the media, because they settle the case. The case is usually about some guy who's been exposed to radiation, you know, a test veteran, or someone in America who worked for some company that exposed them to radiation, whatever. And then after a little bit of argument, and I produce a report, and I bring in the book and so forth, they just say, yeah, okay, have $1 million. Well, $13 million usually is about the normal sum in America in these court cases. I don't get this money, incidentally, before you're looking at me. I get some little pittance, but the lawyers get a lot, and then the person who is ill, or his family, they do all right. And in the United Kingdom, I'm working on several cases for British nuclear test veterans, and some for the Gulf War veterans. So these are uranium cases, basically. And we won a very good uranium case last year, a coroner's case, a chap called Stuart Dyson, who died of cancer. He was a Gulf War veteran, and the West Midlands coroner had a proper full-on case with the jury and everything. It was all in the newspapers, and we won that case. The jury found that his cancer was caused by depleted uranium, and wrote to the Home Office, wrote to the Home Secretary of the British government and said that this is a key case and that you have to do something about it, because that's the law. If a coroner finds that somebody's dead under circumstances which are unusual and that might have an effect on other people, then it is the law that he has to inform the Secretary of State to say that this is the case and something should be done about it. So it's called Section 42. So he did a Section 42 letter to the Home Secretary. And the Home Secretary wrote back and said, oh, well, you know, this is not true. We know that uranium is safe and this chap Busby's a nutcase and so on. But then so the coroners wrote back and said, this isn't intended to be a debate. I'm just informing you under the law that the jury has found that this guy has died because of depleted uranium. So in front of a jury we win. In front of ordinary people we win. And talk to any ordinary person who doesn't know, and you can't lose because the evidence is perfectly clear. So this is a political situation. This is a situation we have to win by using political means.
Is this the only case which was in front of the jury?
Yes.
The first big win.
This is the
Yeah.
first
Okay.
big case. This is the first time a jury has found that depleted uranium has killed somebody.
Yeah.
It should be an absolutely critical decision, that, you know. But the British government, like the ICRB, they just go along like this, see? And they just refuse to. In the old days, what they would do is they say, "Oh well, we're just emotional people, you know. We don't understand the science." That's what they used to say.
They do that still.
And now yes, but I'm not an emotional. Well, I am an emotional. But anyway, I understand the science. And I can play them at their own game, you know. I can use my little calculator to play the science game. And when they lose the science game, they then just say, well, we're not going to talk to you. And this has happened 3 or 4 times now. We've had stakeholder dialogues in England. You know, they have stakeholder dialogues. They say, we'd like to know what you think. And you say, well, actually, this and that. And they say, oh, well, thank you. But because, of course, you know, if you're not a scientist, and they say, we'd like to know how you think, and you go, they say, oh, well, jolly good, very good. Emotional women, off you go. So we win the science argument now, but they still do nothing. But you can all use this as a weapon. You can go to those politicians who are maybe friendly. You can plug it into the European Parliament, because the European Parliament has a lot of power in this area. It can recall the Euratom Directive. The Euratom Basic Safety Standards Directive lays down that if there is new evidence that emerges, it's Section 8, I think. If new and important evidence emerges that these risk models are wrong, then the whole thing has to be reopened. That has to be done. So if you go to Europe, and in Finland, I know you have members of the European Parliament. I knew one called Heidi Haukala, I think she was. I don't know if she's still there, but you must still have some MEPs. So we get to talk to them. We try and get them to put some pressure in the European Parliament. The Swedish Greens as well. Certainly the British Greens are on our side, and the Irish Greens. So we can make quite a fuss.
The Finnish Greens are sitting in the government who just decided about 2 new reactors.
Yes, I know.
So we won't have very much help from them, unfortunately.
No, well,
Unfortunately.
of course, this goes back to the other problem, which is behind all of this, which is the problem of the economic domination of the people by the system. Okay, and let's not go there. But we all know that behind all of this is a huge monolithic economic system which is raping the planet. And this is just part of that. So this is the old war, isn't it? We're back to the old war. But at least we have a weapon to win this war, this battle. And this battle is happening here, in Finland. This is where it's happening.
So, do you have some estimations, or have someone made any estimations about the future, considering public health and cancer rates, for example, for my children?
The nuclear pollution up to 1995 caused 61 million cancer deaths, and about 2 million, it's written in this book, about 2 million infant mortality deaths, and then a whole load of problems due to heart disease and diabetes and a whole range of. What will happen if we stop now and there's no more radioactive pollution at all is the effects of Chernobyl will feed through. That was the last major release of radionuclides to the environment. And the effects of Chernobyl will cause generally an increase in 30% in the cancer rate in the countries that are most affected. That's the ex-Soviet Union countries.
And the most interesting thing is that you can get any disease because of
Yes,
radiation.
yes, sure.
Not
That's right.
only cancer. Cancer is only one flag.
That's right. The heart disease was also a consequence of the radioactive pollution. We know
Because
that.
DNA is damaged and you can get any
Yeah.
disease.
So so you can reckon that there will continue to be an increase in cancer, but it won't go on forever, you see. And the reason for this is because about 1/5 of the population, about 20% of the population, can't get cancer. They have a particular kind of DNA system, a cellular system, which is more or less immune. And the reason is that when it's damaged, there are two ways in which cells behave when they're damaged. One is a way in which they try to repair the damage and they split into two daughter cells. But the other way is they just kill themselves. They cut their throats and that's it. And those people who happily have that kind of cell structure will be more or less immune. So that's why Uncle George, who smoked all his life and drank and bathed in pyridine and swam through benzene and all that stuff, these guys so the nuclear industry say, well, what about Uncle George? So these guys are immune, basically.
So will there be a next level of human evolution?
No, it doesn't work like that. Well, there may be, but it used to be thought, the old system called the clonal expansion system, and this is all new stuff actually, very interesting stuff, a lot of which has come out of Chernobyl. It used to be thought that if you get a radiation dose, a large radiation dose to the population, it kills off the weaker ones, the ones who are radiosensitive, and the other ones are strong and they just march through, you see. That was the old theory, but that turns out to be nonsense. What happens is that all systems respond to these stresses, like radioactive stresses, by developing a system which is called genomic instability. And this is a system in which a message goes to all of the cells in the body, and also to your children, and to their children, and to their children, and to their children. This is like a message which says, mutate. So it's not like you don't get like a mutation A, and then there are 2 cells with mutation A, and then there's 4 cells with mutation A, and all that. That doesn't happen. What happens is you get a mutation A, and all that other stuff happens as well. But what you get is you get mutation B, which says mutate. So the daughter cells of mutation A will have mutation A, B, C, D, E, F, G, F, G, and a whole lot of them. It's a sort of general. It's called like it used to be called the SOS signal. The SOS is now called genomic instability. And also, interestingly, there's a signaler which goes from the cell that's hit to other cells. So this woman, Mother Sill, who is a world authority on this, she's done experiments recently in which she's put fish in tanks, and she's irradiated one fish, and the other fish all mutate. So lots of very strange things happen. And the way in which the reason for this is that populations want to get through, in evolutionary terms, populations want to get through some kind of genetic stress. So if a genetic stress comes, the population wants to think, shit, what am I going to do? And what it does is it mutates in the hope that one of the members of the mutated set, A or Z, or B or Q or M or whatever, is okay. And that one gets through and everybody else is finished, you see. So that's how it's called genomic instability. And it goes down the generations. So in a study that we did of the atomic test veterans, the people we studied their children and their grandchildren. And what we found was extraordinary. It was just like the bank vaults in Chernobyl, because in Chernobyl, the bank vaults, they have 22 generations of vaults which are showing this effect. And in the nuclear test veterans, the children had there was a 9-fold excess of congenital disease in the children of the atomic test veterans, okay? 9 times the national rate. But in the grandchildren, it was 8 times. Now, if it was the other way around, if it was going to be just genetic, because you're diluting it genetically each time, you might see it in the children, but you would see only a quarter of it in the grandchildren. You don't. You see the same number. And I bet you'll see the same number in the great-grandchildren and so on.
So the gene is being polluted for the
forever.
generations?
Well, forever, until what happens is that until those people carrying the signal die before they have children. I know. So what the nuclear industry, what the nuclear project has done is astronomically awful. I mean, it's much, much worse than anybody could have thought. It's created this genetic
damage.
Well, it's like an egg whisk, really. It's like somebody's gone into the DNA of an egg whisk.
And still, if we stop all the nuclear power stations, we still have the waste, which is
We do, that's
polluting
right.
for 300,000
That's
years or
right.
1 million years.
You can put it in a box and look at it. I mean, it is possible. There are things you can do with that waste, you know. You can put it in a tin box and you put that in another tin box and so on. And you put it on a mountain with a notice saying mankind's folly, and you just look at it for billions of years. What you don't do is throw it in the Baltic Sea, which is kind of what the Swedes are going to do.
And Finns.
And Finns, we are further than you, because in Sweden they will start the dialogue in 2014, and we will open up the repository in 2020. So we are the greatest.
Well, let's hope that we succeed before then in stopping this madness.
How much radioactive vapor and particles escape from this intermediate storage is what is the intermediate?
I think that in principle nothing is going. That's what they say.
But to is used nuclear fuel which is put in the weighted water tanks.
Oh, well, they're not open, are they?
Are you talking nuclear waste repository? No.
No, these intermediate depositories.
Well, but I don't know what they do with the intermediate repository in Finland. In England, they have it isolated from the environment, so supposedly.
There is one in Olkiluoto, and you can get a picture of the building and the principle of operation in the internet, but then there is another one in Loviisa, and from that you don't find any information, at least I didn't find.
Well, still, they should measure it. I mean, according to that lady from Stoke I talked to yesterday, they have monitoring systems all around these nuclear power stations, and you can get the data from those monitoring systems. They have, well, they have kind of like a big funnel, and it goes, and the rainwater all washes into something, and then they evaporate it, and they measure what's in there. So
I sent them an email and asked for the data, so what do you think they would say?
You should go on sending them emails till
Yeah,
they
should,
answer,
should,
and phoning them,
it's your right.
and say it's my right. You can even go there. You can phone them and say I will come there to get this data.
It's public data.
So I once asked for data about wind speed, and they said that I should generate the data myself from statistical distribution. Some you get from a mathematics book.
Oh no, yeah, I see what you mean. Yeah, no. Well, those models are nonsensical. Forget those things. Those models are ridiculous. Yeah. You need the measurements. If you want to know what's there, you have to get the measurements, and then you have to assume they're not lying as well.
You have to say that it's your citizens' right, and you go to the European court if you don't get it.
You can get the data, and you can get it under the Freedom of Information Act
Yeah.
and all sorts of stuff.
You can take the Freedom of Information Act as one.
Yeah. We've got some fantastic data under the Freedom of Information Act. Actually, lately, in one of these court cases I'm doing, I asked them under the Freedom of Information Act for all of the reports they had, which had measured radionuclides at the nuclear test sites, you see. So I got this list of reports. So I think there were 65 reports. But unfortunately for them, I already had one report that was a very good one that wasn't in their list, you see. So I wrote back and I said, I'm sorry, but you don't seem to have sent me the report I've already got, which I know you have. And so they said, oh no, that's secret. We're not allowed to give that to you because it's it might affect international relations.
Yeah, that's what they then say.
Because that's one of the cutouts under the Freedom of Information Act. See? So then I went to the judge in this court case that I'm doing, and I said, look, this is no good. So he then sent them a subpoena. He sent them a legal document from the court saying you have to produce it in 2 weeks' time. So then they wrote back and they then said that they couldn't produce it in 2 weeks' time. So there's a big fight going on at the moment. I mean, the silly thing is I've already got the report. You know, so but anyway, yeah. So they'll get up to all sorts of tricks.
I would like to ask about repression of scientists. That in a way, what you're saying is that there is so much scientific evidence, even in peer-reviewed journals, about this high effects of radiation. And so there are so few people like you who are talking openly.
Well, it's about money. It's about money, you know. I mean, they lose their job.
Yeah, and so you are finding that these scientists are being repressed.
Yeah, like Tom Bell. I mean, what happened to Tom? Tom Bell's a very clever young man, you know, and he discovered something something like that. You should make a statue to him out of bronze and put it in the main square in Stockholm, you know, or Uppsala or whatever. He's a very important figure, but he's just been, he's he's not allowed to work in radiation, and they've put him somewhere else where he's working on child health in some irrelevant area, you know. That's what happens. Bandashevsky, who discovered the relationship between cesium-137 and heart disease in the children in Gomel, in the area where he was very important. He was the head of the Gomel Institute, professor. And the Belarusian government arrested him on some false charge and sent him off to jail for 8 years. And we only managed to get him out because the European Parliament kicked up a lot of fuss and Amnesty International, but he was 3 years in jail, you know. And so it's not good for your health to be an anti-nuclear scientist. And the only way I've survived really is because I've been poor for many, many years, and then I've managed to survive through the help of various small charities that keep me going. And then lately, of course, a bit more with these court cases. So if you want to be an anti-nuclear scientist, I can tell you it's not going to make you rich. And the young people nowadays, I mean, I'm sorry, but I mean, these are really great, but most of the young people I know spend their whole time looking on Facebook.
Yeah.
They're not interested in anything to do with it. I mean, it's all too much for them, so they just exchange messages.
But there is a breakthrough in Facebook in Sweden. There was 9,000 members in anti-nuclear Facebook.
Was that?
Yeah.
Okay. Well, maybe we should use that.
Yeah, and then are there more comments that because of you may have a different perspective in this?
Well, we just have the baseline understanding, and I was interested particularly just being a southerner, and we do not have much of these things. But being a Nepali, and we live between the two, of course, now uprising powers, so I just came here because of my interest, but not because of my academic areas. But it's been interesting, and I just have some baseline information being a student of physics in high school, so that's it, so not much of things.
But you did mention that you went to Tanzania.
Yeah.
What did you find out? What did you find out in Tanzania?
Well, there's an Australian company who is hoping to exploit uranium deposits in Tanzania, and there's a small Christian group of local people there who are opposed to this for various reasons, well, for obvious reasons, really. And so they wanted a team of scientists to come and talk about the health effects and the general effects of uranium mining to the local people, because of course there are various tribes who supposedly have control over the areas where these mining operations are proposed. And so we went there, and I took some measuring equipment, and we measured some uranium deposits, and we followed the places where the mining company had been doing its explorations. And I spoke to various gatherings, you know, and to the local people. And they said, keep it very simple. So I remember I said, actually, I lived in Africa, you know, so I speak a bit of Swahili, so, you know, I can talk the language a bit. But I had to say that uranium is an evil spirit from the beginning of time. Do you like that?
Really?
I think that's about it. Really.
Yeah, the Indians in North America have this expression, "Nadatai," that means the death of the stone of death, the rock of death. And they said, don't touch it.
Yeah, so that's right. And it is sleeping in the ground underneath this lake, so you must not disturb it or it will kill your children. It's evil. Anyway, I quite enjoyed that. It made me feel like some colonial guy from the 50s. I expected to have a white hat and all this stuff.
I get one question. So you're basically talking about Africa West, but how does it work to track these things in countries like Iran, which is completely closed,
Well,
and is operating these things?
you can't, is the answer. You know, the Iranians don't have a website where they put down all their nuclear waste concentrations and so on. The most serious problem in that area is uranium. I mean, more than 2,000 tons of uranium has been dropped in Iraq. And we have measured uranium in Lebanon and in Gaza with great difficulty. We had to smuggle some car filters out of Gaza. I was in Egypt talking to Al Jazeera and the Egyptian doctors to get all of this data. And that uranium is a very serious health hazard, and people are dying in Iraq now at a fantastic rate. You're getting women with breast cancer at the age of 20, and you're getting a huge number of congenital malformations in the births in areas where the uranium has been used. And nothing has been done about it. But again, you see, it's the same thing. It all comes back to that risk model. The risk model is the key. And the reason they're doing nothing is they're saying it can't be uranium because the dose is too low. So it's absorbed dose is the problem. You attack absorbed dose and you win.
Did they use depleted uranium weapons in Kosovo?
Yes.
Yes.
I went to Kosovo. I've been in Kosovo. I've actually detected the uranium there and brought samples back and measured them when I was on the BBC. We got these samples before you know. So yeah, sure.
Do you know if these
Afghanistan
weapons
too.
have produce some pollution while storage, or only when in war?
Only when fired, only when used, yeah. If they're in storage, they're okay, they're safe.
But did you then get evidence of Gaza?
Yeah, we did.
Lebanon is clear. I
We
think.
found it in Gaza, yeah.
Also Gaza.
Yeah.
Okay.
And interestingly, what we're finding now is not depleted uranium, we're finding enriched uranium.
Yeah.
But it's, it's slightly enriched, but anyway, it's uranium.
I still want devil's advocate question, because in Finnish discussion, always when you speak about radiation, these authorities start to speak about radiant gas coming from our bedrock and even from concrete walls. And what about this? Is according to your model, also this radiant gas much more dangerous than...
Well, radon gas is interesting, but if we go back to... Well, anyway, if you remember the picture of that man, with the external radiation model for the man, the point about radon is an inert gas. It doesn't react with anything. In chemical terms, it's a member of the noble gases, and it has no affinity for anything. And then it decays to a number of other very fast isotopes called radon daughters or radon progeny, which include polonium-210 and lead-210 and lead-214, bismuth-214. But they kind of go fast. So the radon goes bam, and then it goes bam, 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 and it stops. See? And the point about this is that the radon is equally distributed through the body, generally speaking. It's slightly higher in the lung, so you might expect slight excess of lung cancer from radon. But generally speaking, it's fat soluble, it gets into the lymphatic system, it goes everywhere. So there's no way in which it's concentrated in one place, and it doesn't concentrate on the DNA, you see. So there are some internal, when I say external, internal, there are some internal radioactive substances which act as if they were external because they have uniform disintegration over the whole body. There's no concentration anywhere. So the external dose calculation that the ICRP make is probably pretty accurate. Another example is potassium-14, which they may talk about when they're talking about natural substances. They will say, well, what about potassium-14? In terms of dose, in terms of absorbed dose, potassium-14, which is a natural radionuclide, is probably a much higher dose than the sorts of, a calculated dose that you would get from these substances like cesium and strontium and stuff coming out of nuclear power stations. But it's equally distributed through the body. See, like sodium and potassium, we have the same concentration of sodium and potassium throughout the whole body, and there's no more potassium on the DNA than there is, say, in the cell medium, see, in the cytoplasm. So we can consider some of these internal radionuclides as if they were external, and I think that's the answer with radon. I'm not saying that radon is safe. There's lots of evidence that people who are exposed to high levels of radon have higher levels of all sorts of cancers. Lung cancer is one, leukemia. I've won some court cases in America on radon exposure. But generally speaking, I don't think radon is an enormous problem. It's not as bad a problem as these fuel particles which are not substances because of this dose calculation way of seeing it. And a lot of the radon studies that show lung cancer are also studies of miners, you see. So the miners have high levels of lung cancer because of their because of their exposure to radon, but they're also exposed to radioactive particulate dusts too, because it's a very dusty business being a miner. You know, they get choked up with dust, and a lot of these dusts are radioactive. And the uranium miners, who have the highest radon, also have uranium in their lungs. So it's not just the not just the radon that's the problem there. Okay.
Excuse us. So there will be another panel discussion on floor 4, 42, room 42. So we shall have to go and prepare. This is via Terjau from Belgium. Thank you. So welcome.
Yes, I think that we want to follow that discussion about uranium weapons, and I think that Chris, you participate in that discussion. I think that was really very cool.
Have we got a projector?
Probably, but we can check and take this one. It's not available.
Chris, can I pay a bill for